Why hello friends, Jen Foxbot here. Welcome to another edition of Math Mondays, da 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 da, yeah! Alright, in the last episode we looked at how to calculate center of mass for a, one-dimensional object. And in this episode we are going to tackle two-dimensional objects, and we're going to look at how do we deal with non-uniform mass distribution. So, okay, why should we care about this? Well, center of mass is really important to understand how objects behave under different types of forces. So for example, I used center of mass calculations to figure out how stable different types of objects were in parkour. So there was a parkour gym in Seattle and they made lots of different shapes of objects and they weighted them differently, like by adding weights in the bottom of these objects. And they asked me to calculate how stable these objects were and at what point would they tip over. Super important. You want your athletes to be safe and also be able to have fun. So that being said, yes, we will build up to stability analysis of different objects, but we have to understand how to fully calculate center of mass so that we can deal with whatever real world scenario that we are given. Okay, so in the last episode of Math Mondays, I gave you the challenge to calculate the center of mass for a two-dimensional object of a rectangle. Bloop. And like a good physicist, I gave you variables instead of numbers. The reason why I like to do this is because it allows us to generalize. It doesn't matter if our rectangle is teeny, 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 tiny or really, really big. What we're really interested in here is ratios. What is, the ratio for the location of the center of mass? Because then we can just scale our object and that location basically stays the same as we scale it. So our object is going to have height h and length L. And the first thing that we have to do is set up a coordinate system. So I'm going to set my origin to be 0 at the bottom left-hand corner of the box. In the horizontal direction is going to be x, and in the vertical direction it's going to be y. Okay, so now we have to pull back our equations for center of mass. And so let's start by the equation for a continuous center of mass. In a particular direction, we'll just say, generally speaking, x. The equation is that we are going to integrate or add over the whole mass. And so it's going to be the length of the particular chunk that we are looking at times the tiny amount of mass in that little chunk divided by the total mass. And then basically, again, this is a weighted average. So just to refresh our memories, what this means is that we are adding up teeny, 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 tiny slices. That's what this D means in DM. It's like, okay, we're going to take the tiniest slice of mass that we possibly can, and then add up all of those slices for the total length of the object. So in this case, we found that the tiny slice of mass is going to equal the total mass of the object divided by the total length of the object times the tiny, tiny, tiny width of the object. And the tiniest width of the object that we could possibly make is dx. And so if you have looked at or studied physics or engineering before, you might recognize that the total mass divided by the total length is also called the density. Yay! So density is represented by the Greek letter rho, which is basically like a little p, but without the extra top part of it, I guess. I don't know what to call that. So density in one direction is called linear density. So for a linear density, it would just be the total mass divided by the length. But in this case, we have two dimensions. And so instead of a linear density, we have an area density. So the density becomes m over a, where the area of our object is just h times L. Okay, so now that helps us recognize that dm is going to change to reflect the area. The other thing that we need to recognize that's really important is that we are going to have to do this 2 times. One, we are going for the first part, we're going to add up teeny tiny slices in the x direction, and then in the second part, we're going to have to add up teeny tiny slices in the y direction. The important thing to note here is that when we're going in the x direction, the length of our tiny slices has a length of dx. But the height of these slices as we go this way is actually h. And similarly, when we are going in the vertical direction, the width of these teeny tiny slices is dy, but the length is L. So this allows us to do 2 integrals, one for the center of mass in the x direction and the other for the center of mass in the y direction. Okay, so we are now ready to combine our understanding to find the center of mass. All right, so the first one, let's do x. And so we are going to take this general equation over the whole mass of the object, x dm divided by m total, and we are going to substitute in for the area density, as well as instead of dx, we are going to have dA. So this is going to be from 0 to L, x times the density, which is m over h times L, times dx times h. And we divide by the total mass. And the nice thing about this is that a bunch of stuff cancels. So these m's cancel and these h's cancel, and we are left with the integral from 0 to L of x over L times dx. Wait a second, this is basically the same thing we had last time. Heck yeah, it is. So I'm going to say ... we've already done this, and we're going to get 1/2 L. Boom! No big deal, right? So now we just repeat this for the y direction. And what's really nice is that in doing it in this way, we basically get to do the same thing, we just change the appropriate variables. So we'll start from the general equation, 0 to m, y dm over m total. And so in this case, we're going from 0 to h, 0 to h times y, appropriate density, h times L on the bottom. And in this case, we have dy times L, and then all divided by the capital M. And again, a bunch of stuff cancels. Woo! I love when things cancel. Make our lives easier. Okay, so from 0 to h, y over h dy. Look at that. It's got the same form factor. So boom, we have our answer, 1/2 h. Not so bad, right? So now the coordinate for our center of mass of this rectangle is just 1/2 L, 1/2 h. Oh yeah. Boom, just what we would expect. The center of mass is smack dab in the middle of our rectangle. Yay! Okay, so that's what happens when we have a uniform distribution of mass. But what if I were to tell you now that instead of, a box that was made out of the same type of material, what if we had like lead in the bottom and wood on top, so that 75% of the mass was in the bottom half and 25% was in the top half? This is called non-linear distribution of mass. And check out part 2 to see how we calculate that. Yeah, all right, part 2, here we go.